Hello, good morning. Thank you for joining us and welcome to Raycastle's latest live webinar looking at 4G and 5G critical communications systems interworking. This webinar aims to clarify why there is a requirement for interconnecting legacy LMR technologies with 4G, 5G systems and explains the steps taken by the 3GPP and the relevant LMR standards authorities to facilitate internet working. We'll also highlight some of the challenges associated with interconnecting networks, possessing operational and functional requirements and service limitations that are so different. First, a brief introduction to Raycastle for those of you that don't know us. We empower the global telecoms world by developing the specialist knowledge, skills and competencies organizations need to build, maintain, optimize and operate the cutting edge communication networks of today and tomorrow. We were founded in the lovely Raycastle, which you'll see here in 1958, and we're still HQ'd in the English Lake District, but we do, however, train worldwide. We're the preferred partner for many telecoms and high-tech industry giants and adjacent industries, just a few of which you'll see below, including some of the major UK mobile operators and international operators as well. Our extensive training portfolio covers all the major technologies, including 5G, LTE, IP, virtualization, etc. And we deliver this training to a wide range of audiences, from highly experienced engineers to new starters in the industry and those with a commercial background. Now, how do we deliver this training? Through a number of flexible learning solutions, including traditional instructor-led classroom courses, which are delivered, on location, face-to-face, live virtual classroom training, such as this one, which delivers the same experience you get as in a traditional classroom setting, but without the need to travel. We also deliver self-paced distance learning courses, which are on demand, and you can learn anytime, anywhere, on any device, and you really control your learning as and when you need to do it. And also enterprise-wide academies, which are designed and customized for each client and make our training available to people across the business. Now, before we get going, I'll just introduce you to our trainers today. Today we have two trainers. We have Les and Carl. Les is a technical trainer with over 35 years of experience. His expertise extends across a wide range of telecoms technologies. He specializes in GSM, UMTS, LTA radio access networks, radio planning, network optimization, and push-to-talk over cellular. Carl is an experienced training specialist in radio theory, point-to-point, point-to-multiport, and mobile systems. The presentation will last approximately 30 minutes. If you have any questions, please post them in the chat box, and Les and Carl will answer them at the end of the session. If you could all please ensure that you keep the microphone muted throughout the session, just to make it a little bit easier for the presenters. So that's it from me. So I shall now hand over to Les and Carl for the main presentation.
Good morning, everybody. It's Carl speaking here. I'll be delivering these slides, as Paul suggested, between myself and Les. I'll be starting off this presentation with slide 1, and then Les will alternate across a series of slides. The first slide here looks at the whole issue really is the fact that we have legacy networks all over the planet, really, into traditional LMR style. Predominantly voice-centric with some data facility and applications. The issue, of course, usually is the bandwidth here. So we have limited bandwidth on this air interface. In other words, narrowband systems. What we also tend to associate with LMR networks is the dispatcher function, or operator, if you prefer, usually referred to as the dispatcher, which is distinctly different from a more commercial cellular operation. So the distinct differences are dispatcher operation, narrow bandwidth, and then other service requirements, such as group calling and so on. If we look at the cellular world, and we're talking here about LTE and moving on to 5G, this is a heavily standardized industry here. Where the technology is heavily standardized and the network architecture is heavily standardized. And these are designed, of course, for commercial operation initially, although on here it says private network. Of course, we can use these now for private networks, this technology. But the initial impetus was a commercial grade mobile broadband technology. And there's the key word. This here is a much bigger, higher capacity pipe or channel than what has traditionally been enabled on LMR networks. The core network of 4G, 5G is, of course, all IP, including the UTRAN. And so there's distinct differences there as well, whereas this might be more associated with a circuit switch network. However, over the years, we've seen the LMR core networks develop into all IP networks as well. Now, as usual, the nice thing about standardization is there are so many standards to choose from. We see here some of the LMR systems, legacy systems that are in existence in the market and used by various user groups, user organizations all over the planet. And in this column here, we see the standards body, if there is one, associated with that technology. Tetra, we associate with ETSI, P25 with TIA, and so on. Some of these technologies are more the open standard format rather than to an official standardized body. So things like NXDN, which was originally a Kenwood and JVC joint operation, and Tetrapol, and then various analog FM technologies, all open standard, usually actually standardized or regulated by a national regulatory authority. So the issue is, the key issue here is this is broadband, this is narrowband. And the traditional users of narrowband technologies, usually we associate these with critical communications, etc. They are very interested, of course, in this broadband capability for certain services they might like to use. However, this network architecture and services wasn't originally configured to support all the other use cases and services that the LMR network users would like. However, the standard body, 3GPP, decided to dive into this area, and they have created a series of releases over the years, which have gradually expanded the capabilities of the traditional commercial LTE network to support traditional mission-critical requirements, such as group calling, press-to-talk, and so on. So the issue now is then, well, if I want to retain this technology, because I've invested in it, but would like to also use this technology, would it be feasible to allow these two networks to interwork? And of course, that's the purpose of this session, looking at this interworking capability. So what I'll do now is I will then move on to the next slide and ask Les to take over.
Thank you, Carl. Hopefully everybody can hear me as well.
I can.
Right, okay. So 3GPP, the third generation partnership project, are the driving force behind the standards for mission critical communications and of course the IWF, the interworking function. 3GPP have published a technical specification, TS 23.283. That's shown on the slide. And this particular document is entitled Mission Critical Communications, Interworking with Land Mobile Radio Systems. If you have a look at this document, you will find it describes three interfaces known as IWF1, Interworking Function 1, IWF2, and IWF3. If we take a look at IWF1, this particular interface was actually specified way back in the early days of 3GPP, Mission Critical, Release 13, and it specifies a way in which mission critical push-to-talk servers could be connected together. So we might have an MCPTT server in one organization's network, and we need to connect that to another organization. So IWF1 was to interconnect those servers together. The MCPTT server is the device that's going to support mission critical communications, whether it be point-to-point calls between individual users or possibly group calling. But the MCPTT server is central to the operation of the mission critical network. So it makes sense to perhaps use that IWF1 as a means of interfacing the MCPTT server to an interworking function. In release 14 of the standards, 3GPP introduced mission critical data, and we have a MC data server, which we'd also perhaps like to connect to a different organization. So we introduced the IWF2 interface. And thirdly, the IWF3 allows us to connect to a group management server. The group management server is part of what's called the Common Services Core, and this is going to be essential if we wish to set up group calling. Quite commonly on LMR systems, point-to-multipoint connections, group calls are the common practice. So we need to be able to set up our groups, so-called talk groups. We need to affiliate to those talk groups. We need to be able to register and deregister, de-affiliate, and manage those talk groups between systems. So between users on a mission critical network and on a land mobile radio system, an LMR system. Now, interestingly, when you look at 23.283, even though it defines those interfaces, it doesn't actually define or describe how the IWF works. Okay, it only describes what the IWF should be able to do. And I'm going to pass this back to Carl now. Perhaps you can just give us a few words about what the IWF should be capable of doing.
Thank you, Les. So on this slide, we see, I guess, all of the things that we expect from a traditional LMR type network, or mission critical network, if you prefer, that we might not necessarily associate with a classical commercial network technology. Now, of course, one of the things that we would expect on both is the individual call. So we might think that's relatively easy to facilitate between two networks over the IWF, the ability for one person to call another and have an individual call. However, of course, we associate on the LMR network this being more likely to be a push to talk call. So of course, that has to be incorporated in the IWF, this mission critical press to talk facility that Les was just talking about. Also, we see something which we associate with both types of network. In the LMR network, it's usually referred to as a short data service, tends to be a generic name for that kind of thing, or status message. You might have heard that expression. In the commercial world, we might refer to that as texting. Now, of course, on the LMR networks, we've been able to build dynamic text messages dynamically, but there's a slight difference. In the LMR world, we tend to have predefined status messages, predefined text messages, if you prefer, to be delivered across the network from one user to another or one user group to another. It simplifies the process and speeds things up if they're predefined. Now, I mentioned they're individual and then group. And here's the big difference. We have to support group calls. Okay, well, we've done that on the LMR, in the LMR world for years, for decades. But it's a relatively new concept to the commercial network world. They probably associate more with a conference call. But a conference call is the right sort of idea, but it's very resource intensive, using lots of channels. In an LMR network, we operate group calling much more efficiently to enable that facility. We want to be able to now to enable a group call to and from an LMR network, to and from this LTE network or 3GPP network. Something else we've been able to do on the LMR networks, and we'd like to continue doing, is linking groups or regrouping, where we can link two groups, maybe on the two different networks, even dynamically. So can we do that across LMR to LTE? And group attach, where we can already have a pre-existing group on either the LMR or the LTE technology, and can we then bring somebody in to that group, also maybe dynamically. Something else that's an issue and slightly different to the traditional cellular network is the idea of emergency calls and preemption, prioritization or interruption, okay, and call queuing as well, where supported. We tend to refer to those in the LMR world as transmission control, and it's something that's relatively new to the commercial network world. So that needs to be supported as well by the IWF. And last but not least, a really hot topic, which obviously has massive security implications to some user groups, is this whole topic of encryption. Can we encrypt network to network? That might appear to be something you might consider to be straightforward. And, you know, why not? The mobile phone networks, commercial, have been encrypted for some time, as have the LMR networks. But I'll talk more a little bit about that shortly. We'll talk more about that shortly. Expand on that. So those are the things that we'd like the IWF to be able to do between the two technologies. And having covered that, I hope to your satisfaction, I shall pass this back to Les.
Here you go. Okay, on this slide then, on the left-hand side, we've got in green our LTE network. It's labeled a private network. We saw that term a little earlier. Mission critical networks are going to be private networks. You know, we don't want the general public using a mission critical network. But on the right-hand side, we're looking at the Tetra system. So, you know, we're focusing on interworking between LTE and Tetra. Now, within the Tetra network, the core network is referred to as the SWMI, the switching and management infrastructure. And the SWMI is largely proprietary. One of the things about Tetra is only the interfaces into and out of the system that are actually defined by the Tetra standards, the ETSI standards. So the SWMI is a proprietary system. However, ETSI have defined a way of actually interconnecting different Tetra networks together using a system called the ISI, the Inter-System Interconnection. And it was designed to connect, you know, Tetra networks together across international borders. In the early days of the standards, that ISI was based upon 2 megabit transmission lines. It was a TDM system. But these days it's based upon IP in line with the rest of the telecommunications world. So it would make sense perhaps for ETSI to define the interworking function. So I've drawn the IWF box inside the Tetra system. So it could be based upon the ISI as mentioned, and of course using the 3GPP defined interfaces, IWF1, 2 and 3 as shown in the diagram. Now, ETSI have partway developed some standards with regard to interworking. The document to have a look at is the technical specification 100.392-19 as shown in the slide. There's 2 parts to that particular document. Part 2 deals with speech transport, and that is now complete. But the first part of the document, which deals with protocols, it is not yet finished. So this is clearly going to be a work in progress. Overall, the idea is that the Tetra terminal, if he wishes to communicate to a mission critical user, will actually think he's just talking to yet another Tetra user. And likewise, a mission critical user should be able to communicate with the Tetra terminal as if it was just simply another mission critical user. But we have a couple of issues. First of all, the speech codec used in Tetra is not the same as the one used in LTE networks. Tetra uses the ACALP, the algebraic code excited linear predictive codec, whereas an LTE network is likely to be using an adaptive multi-rate codec or possibly an EVS codec. So the interworking function will need some means of transcoding between those 2 speech formats. The other issue is security, as hinted at by Carl in the previous picture. What I'm going to do now is pass it back to Carl, and perhaps you can sort of expand a little bit upon the security issues interworking LTE with Tetra systems.
Okay, cheers, Les. Now, in the Tetra standards, the encryption that's applied or is defined in the standards is air interface encryption. So in other words, the methodology used for encrypting the connection between the radio, the mobile and the base station is defined in the standards, and that's Tetra air interface encryption. So In other words, from the base station into the core network, the SWIMI, then the speech would therefore be in the clear if you only applied Tetra air interface encryption. However, Tetra is capable of supporting end-to-end encryption within the Tetra SWIMI. Now, this could be a proprietary encryption algorithm, which is installed on each mobile and allows mobiles to communicate with each other with all of the data, the signaling and the voice, if you so require, all of those to be encrypted. They can be encrypted end-to-end, and you can apply a proprietary or your own encryption technology. Now, most of these encryption technologies need some sort of synchronization mechanism so they know where they are in the encryption routine. And the Tetra standards do specify how to support that synchronization technique methodology. So the synchronization is set in the standards. The actual encryption technique you use can, in effect, be up to you. And that's all well and good, of course, when it goes from one Tetra mobile out to another Tetra mobile. We could support Tetra end-to-end encryption, no problem. But when we go through the IWF, we will hit this security gateway on the 3GPP side that interfaces to the 3GPP system, So what we can do is we encrypt end-to-end all the way through the network or just over the air interface and strip that encryption off on the security gateway and then pass it over to 3GPP network security techniques this side. Now, this, of course, creates a bit of an issue from maybe a security perspective, which is, how do we handle security keys? How does this, well, basically that's the issue. How do we handle the security keys? Do we want to go through a de-encryption process here and then an encryption process there? We might have to. Or if we are going for end-to-end encryption, do we want to take this Tetra end-to-end encryption all the way through to the 3GPP mobile here? Now, that can be supported. That's not a massive problem. It's catered for. But to do that, the 3GPP mobile here must support the Tetra codec. There's no other choice because the voice was coded here on the Tetra mobile using the Tetra codec, passes through the entire system, or systems in this case, and is decoded here, where they must, of course, support the codec, otherwise they won't be able to understand the voice. So that's the key issue there. The 3GPP mobile must be able to support the AKELP codec, as Les mentioned. So the decision on what to encrypt and where to encrypt will, of course, be an operational decision made by, usually, of course, the mission critical operator themselves. How much encryption? Do they want just the air interface encrypted, end-to-end encryption across Tetra, or end-to-end encryption across Tetra and through to LTE? And if they do want that latter one, they must support the AKELP Tetra vocoder on the mobile device on the 3GPP network. So that's the key issue there from the security perspective. And I shall now hand back over to Les to talk us through the issues associated or catered for in the P25 system.
Thank you, Carl. Yes, P25 is another major LMR system, not used much perhaps in Europe, but certainly in the United States. And you may be aware in the US, there is actually already an existing LTE mission critical network, which is referred to as FirstNet. But their dominant LMR system within the US is P25. So there's clearly a need for being able to interwork between P25 networks and mission critical LTE networks. So once again, this will be the job of the IWF. So on the left-hand side, we can see our private network, LTE network. We've got the 3GPP defined interfaces, IWF 1, 2, and 3. But on the right-hand side, we need a means of interfacing to these P25 networks. Now, there is an organization called ATIS, which is the Alliance for Telecommunications Industry Solutions, which is an American standards development organization. And they develop technical and operational standards. And there's also the TIA, which is the Telecommunications Industry Association. And they're a standards development organization that develops voluntary, consensus-based industrial standards. So together they have come up with 3 potential interfaces to the IWF. And they're shown in the diagram, starting from top to bottom. We have L102-T, which allows you to interface a trunked P25 network to the IWF. We have L102-C, which allows us to interface a conventional P25 network to the IWF. And then L603 at the bottom would allow us to interface conventional analog networks to the IWF, but that has not yet been fully defined. So the major features which LMR users expect to be able to use, as Carl mentioned, are group calls, emergency group calls, emergency alerts. Need to be able to set up private and individual calls. Clearly, we need to support encryption as well. That not just applies to Tetra, but also to P25 networks too. And we need to be able to manage sort of user identities and group identities. Now, the TIA have gone some way in actually being able to interface P25 networks together. There are many P25 networks in the US, and there's often a need to be able to actually interconnect those networks together. So if I can ask Carl to pass me over to the next slide, please. Not sure who Clive is. So the TIA have come up with a standard for interconnecting P25 networks together. The little fluffy clouds in this diagram are labeled P25 RFSSs, which stands for a radio frequency subsystem. And an RFSS might be used one emergency organization, and it would be useful to connect that to another emergency communications network. And that's the job of this ISSI, which is the inter-system, inter-RF system interface. It's an IP-based connection, and it allows you to create a system of systems. And as mentioned, it's defined by the TIA. So they are in possibly the best possible position to define the interworking function, possibly based upon how the ISSI works. Also, on the right-hand side of this diagram, there's another version of the ISSI called the CSSI, which is an IP-based connection allowing us to connect the control room. So we've got the control or console subsystem in the control room connected through to the radio frequency subsystem over the console subsystem interface. So again, potentially that could also be interworked into the IWF. But coming back to Europe, perhaps, and if I could ask Carl to pass me the next slide. There is another mission critical network that some of you may not be aware of, and that's called GSM-R. GSM-R is a radio communication system used by the railways for essentially communications between perhaps a train driver and a signaller, or perhaps between railway staff members. It's based upon the second generation GSM-R system. It's had to be adapted because GSM-R was essentially a point-to-point mobile telephone network, and we've adapted it to be able to support group calls, for example, not just simply point-to-point calls. So the manufacturers of the GSM-R equipment have stated that they no longer wish to support their products beyond the year 2030. And because railway communications is important, we really do need a successor for GSM-R. Now, there's an organization called the UIC, which is the International Union of Railways, and they have recognized there is a need for a successor for GSM-R, and they proposed a solution called FRMCS. FRMCS stands for the Future Railway Mobile Communication System. They haven't actually specified a technology. They deliberately have said that the FRMCS system is going to be technology agnostic. So the early thoughts were it could be based upon mission critical LTE, as these systems are already in existence. I've mentioned FirstNet in the US. We've got the Emergency Services Network, ESN in the UK, and there are other examples globally. However, it's going to take a number of years for FRMCS to come to fruition. And of course, we've got 5G today. So you could argue, well, there's little point perhaps building a replacement for GSMR based upon 4G technology. Let's go straight to 5G, and that is likely to happen. But we're still left with a problem. You can't simply just switch off GSMR at midnight and then switch on the replacement a few minutes later. The two systems will have to coexist for a number of years. So once again, we need an interworking function so those two systems can intercommunicate. So 3GPP have specified something known as the IWFR. So it's the interworking function for railways, but it used the same three interfaces we mentioned previously. So IWF1, connecting through to the mission critical push to talk server, so we can set up point-to-point calls and group calls. We need that IWF2 and IWF3, so we can connect to the group management server and the mission critical data server. So this is the solution that's been proposed by 3GPP. You can find details in the technical specification 23.283. However, the protocol translation within the IWFR is out of the scope of 3GPP. So it is likely that ETSI will take over this particular role because GSMR is an ETSI-based standard. So ETSI will provide the necessary framework. There are other sort of more detailed issues. For example, within a railway network, we use function numbers. So a train on a particular journey is identified by a function code or a function number. A signaler will also have a function number as well. And function numbers are specific to GSMR, and they wouldn't be recognized by a mission critical L2E network. But what the standards have specified are functional aliases, which would be a nice way of mapping function numbers to LTE identities called functional aliases. But we are still left with problems with encryption. End-to-end encryption is not going to be possible between GSMR users and mission critical users. The other problem is GSMR doesn't support talker location. One of the things specified in the FRMCS world is the fact that we should be able to actually identify the location of the train from where the call is being made. That's done in GSMR, but it's not something which can easily be done in an LTE network without some consideration. GSMR also does not support floor control. Floor control is something which we find in MCX, mission critical communications. It basically controls which participant is actually allowed to speak at any one point in time. So if we have a group call in progress, we only want one person speaking at one point in time, and that's managed by a floor control protocol. Well, GSMR doesn't have a floor control protocol, so the IWFR will have to manage that interworking somehow. And when it comes to the short data service, which is commonly used on Tetra, or SMS text messages, well, they are for further study. So if I can pass the control back to Carl.
Thank you, Les. One point I wanted to mention just before we leave this slide, and this applies to all LMR to LTE interworking, is the data server, mission critical data server. So ignore the fact that this slide is leaning towards GSMR. This applies to the technologies we've talked about already, Tetra, P25, etc. The decision has been made that no matter what we do, we can't work miracles and we can't change the limited bandwidth on the LMR side. So the limited bandwidth we associate with LMR, that stays. There's nothing we can do about that. We just haven't got the bandwidth. So the decision has been made that the mission critical data server is really aimed at the transport of short data service messages and small data files, not the transfer of mission critical video or large data files, etc. It just can't be done. We haven't got the capacity on the LMR network. So that really is the focus of the mission critical data server. Okay. so far, we've talked about the IWF as specified by 3GPP. But the IWF has been specified. The Tetra world, in the P25 world, etc., they're still working on those interfaces, as we've indicated already. They're not quite completed. Now, this slide here looks at some of the things that have happened in the States. I think it was, yes, the year 2020, as you can see at the top of that little map there. It's just 2020. We have these $1 billion plus weather and climate disasters. So here we're just talking about climate. And you can see some of these would be relatively, or you can imagine, some of them would have been relatively localized. Some of them would have been over wide areas. And when you get this type of incident, unfortunately, it involves a lot of organizations. We can imagine instantly, can we not? Fire, police, ambulance, and so on. But then you also got your things like mountain rescue, the Coast Guard, etc., etc. And we get a whole host of organizations involved in responding to these events. So we see here, we get statewide organizations, organizations that are associated with large metropolitan areas, and indeed some county or local systems. Now they, I'm afraid, over the years have gone their own way on their choice of radio system. I'm sure there are technological constraints. I'm sure there are budgetary constraints. But the point is, we are where we are, and we see this amazingly disparate number of radio systems used by these organizations. And this will be the same in a lot of countries around the world. So we see on these circumstances, wildfires, hurricanes, etc., there'll be interagency working. So we see this mutual response required between these organizations. But they've all got different radio systems, or potentially all got different radio systems. And they saw this as creating a massive problem in rescuing people, etc., and making people safe. But we might be sat here thinking, well, we've got the interworking function. Why don't we just interconnect them with the interworking functions between LTE, the first responders network, as Les mentioned, and so on? Well, the standards aren't finished. Now, a lot of these organizations couldn't wait, okay? And they decided to go down another route, which is on the following slide. And that route is called, rather strangely, radio over IP. It's cheap. On a relatively small scale, it's cheap. As you spread it out, it gets more and more expensive. So let's have a quick look at how it works. Excuse me. So over here, we have an LMR group call taking place between these mobiles over here. Now, if you notice, one of these mobiles is referred to as a donor mobile. You see that there? A donor mobile. And that mobile will be fixed in one specific location where it gets good coverage from the base station and will be part of that group. Next thing to notice is the donor mobile is hardwired in to this relay unit here. So the relay unit takes the messages, signaling messages from the donor mobile that it receives. You know, maybe this mobile here set up the group call, and it takes that group call message, passes it to the relay unit, and the relay unit will feed it through this IP network, because the signaling message will have been packetized, to this relay unit here associated with other members of this group who are on another network, this LTE network. The relay units here will then create a group call message in LTE speak, if I can use that, pass it through to this donor UE, and the donor UE on this side, again, in a fixed location, hardwired into a relay unit, will then set up the group call in the LTE network. And then we can exchange packets of voice and signaling between this group and this group like so. So this became a solution that a lot of organizations took on board to facilitate a way of interconnecting networks whilst they waited for the standards, the official standards, if you like, to be developed. Now, you can probably see that this can get expensive because you've got a lot of subscribers and a lot of groups. Each group needs a donor mobile. Okay, not just each network, each group in the network needs to have an associated donor mobile, which will respond to the group call request and then pass the messages through the system as I've just explained on both sides. So we need a donor UE this side for each group on the LTE side. So you could probably imagine the expense that could be generated with this technique. But if it enables the straightforward passing through of voice calls, which is all it does, by the way, voice calls only at the moment, then we've resolved this problem in the interim period whilst the standards are finalized and then brought into use. Okay, so I hope that made sense. And on that note, I shall say we've kind of finished the material.
Thank you, Carl. Thank you, Les. And thank you everyone for attending. I hope you all enjoyed that webinar and look forward to welcoming you on the next one. Bye.